carry on. So there's one last example that I owe you from last time. Where do two curves cross each other? And this won't be anything deep. So let's suppose I ask you, what are the x? So what are the points of intersection between this graph and that? So you know just by looking at it, that'll be like a straight line. That'll be a parabola. In fact, maybe it's all seeing these two things as graphs. So, how many points of intersection do there appear to be? 2. And in fact, maybe you believe that should be like generically true. If you take a parabola and intersect it with a line, you believe there will be like 2 or 1 or no points of intersection. So let's try to find them. On the one hand, it looks like one of them's an x value of around 0.3. The other one, I guess it's telling you exactly what they are. Well, no, that's still an approximation. A negative 3.03. So let's go through the walk of finding them. And the only deep idea is if you have two lines, two curves that are crossing, what that means is you're looking for points x, y which satisfy both equations. So you're looking for x, y points which satisfy both of those equations. In particular, those two y's have to be the same. So you get that as a result. That as a result. Does that look like an equation we can solve? Yeah, I guess the first thing to do is get all the x's onto one side. So let's see, I guess that becomes add 2x to both sides, subtract 3 from both sides. And once you want to see an equation like that, what strategy would you like to use to solve it? Yeah. Great. You have, that's definitely a hammer that can be used to hit this nail. Let's do it. So, by the quadratic formula, there's my choice of A, there's B, there's C. X is equal to negative B plus or minus the square root of B squared minus 4 times A times C, all over 2A. That was quick, but I think I jotted everything down correctly. Groovy. And I don't see any simplification. The whole numerator isn't even, so I can't cancel the 2. The 13 under the square root has no square factors. Alternately, does anyone notice anything that I screwed up? So that's possible too. Nice. And then, well, if you want to know what those two x values are approximately, let's approximate them. Point. 303. Good. So that was just me jotting those down. So I guess that tells me the x values of the points of intersection, doesn't it? So the points of intersection are at x equal to 0.303, approximately, negative 3.303, approximately. Given the x values, how could we find the y values? Plug it in. I guess I have two formulas. If these are actually points of intersection, they should give the same result. So I guess we should pick the simplest one to plug into. Maybe we'll do an extra one as a checksum. So 3 minus 2 times 0.303 gives me a y value of about 2.39. I know you can't see what I'm writing, but I'm just trying to copy down those same numbers in the y coordinates. Everyone feel pretty good about that? So, and now let's just make sure we've actually addressed the prompt. Does this question explicitly ask for an exact answer? I hope it doesn't, because I haven't given one, have I? Right, the actual exact answers would involve some square roots of 13. Groovy. So that was pretty quick, but hopefully the idea is not too deep. Groovy. So let's keep on going. So today I want to, so there's the extra credit sales pitch. I'm not going to talk about that ever in class, but you'll come by my office, tell me about it, and you'll get some extra credit points. Anyone planning on taking me up on that? Good. The official deadline is the last day of the semester before finals week, when I go home. But you shouldn't put it off till then because I'll get busy, and if I just don't have time to talk to you, you don't get your points. So let's set it up. So if I say, how many people have read the short story, How Much Land Does a Man Require? It's a work of Leo Tolstoy, a Russian classical work, so it's obviously going to be depressing. So let me give you the brief portion of it. So this guy, Paco, makes a deal with the devil. He says, "Devil, I'll give you my soul in exchange for you giving me all of the land that I can get," or something to that effect. And so he goes about his life. He gets stuff. He gets greedy. You have an idea. And he comes across a village of people who offer him a very novel trade. He gives them some money, and then as much land as he can walk around, circumnavigate, from sun up to sundown, he gets to keep. So he says, "Great, I can do that." And close to the end of the story, you can tell that things are going to end badly for him because this is a work of Russian literature and it involved a deal with the devil. Tropes must be obeyed. He goes very far. He pushes himself too hard. He finds himself too far from his destination. The sun is beginning to set. So he rushes back to get to where he started so that he will actually have circumnavigated a piece of land. Otherwise, they get to keep his money and he doesn't get anything. And so as he's coming in, they're cheering on his good fortune. Nicely done. He makes it to the finish, and so gets his land and drops dead immediately of exhaustion. And I think the final line, in at least the translation to English that I read at some point, is, "And so he discovered that the amount of land that a man requires is about 6 feet by 2 feet." Now, there are questions that this brings up, like ethical questions. How much land does a man require? Maybe you shouldn't be greedy all the time. Let's ask a more practical question. How much land can this man acquire without dying? So, let's bring to bear some of the techniques we have. So we'll make a few simplifying assumptions. Paco will try to enclose a rectangular region. All right, that's a reasonable simplifying assumption to make. And he has also, by walking up his endurance, found that he can reliably cover about 40 miles during the course of sundown to sunup. That doesn't seem ridiculous, I hope. If it is, it doesn't really matter. I hope no one's planning on selling their soul to the devil and using this analysis as the basis of their future decisions. Good. So, let's try to answer the question. And let's start by modeling it. He wants to capture land in the shape of a rectangle. Let's draw a rectangle. And a rectangle has like two parameters, right? Length and height. Maybe it's silly to call it height if it's a rectangle that's like on the ground. So let's just call the dimensions of this rectangle x and y. And he knows that he can cover 40 miles. So presumably he's going to try to capture a rectangle of perimeter exactly 40 miles. So let's write that down. So I know that 40 is the ideal, the maximum perimeter that he can use, and presumably bigger perimeter will result in bigger area. What's the formula for the perimeter of a rectangle? Yeah. 2x plus 2y. And alternately, if you just don't like formulas, xy, xy. So 40 is 2x plus 2y. Does that look like something that we could solve for one of the two variables? Yeah, do it. What is x or y equal to in terms of the other Gesundheit? So I have this equation, 40 equals 2x plus 2y. Does that look like something that you could solve for, say, y? Yeah, and I don't want to do it, so I just want you guys to have already done it. What is y? Yeah.
20 minus x.
I hear 20 minus x. So the reason I did that is right now the analysis involves two variables. And you can do analysis over two-variable problems. You need some more sophisticated techniques. And so I'll just try to imagine away one of the variables to begin with. So now I have this. This parameter y is given by 20 minus x. What's the area of a rectangle? X times y. It's base times height, and those have names. So the area, which is probably relevant, that's the thing we're going to try to optimize, is equal to the product xy. And I want to make that as big as possible. But there are constraints, right? You can't make x and y both be independently arbitrarily big. You have this perimeter constraint. So let's apply that. So there's the area, the thing I want to maximize. I have a formula for it. Cool. So far that makes sense? Well, we have an idea what the graph will look like, right? It'll be like a downward opening parabola. So the graph will look something like that. By looking at this parabola, if I want to maximize the output, like what point on that parabola should I take? Yeah, the vortex, the point at the top. So I want to find that vortex. So maybe it would be useful to have a graph to look at. So let's graph that by using the techniques from last time. So let's, I guess, complete the square. And maybe this is another good chance to just recall the completing the square technique. So, sorry, the completing the square idea, I'm going to show it in more gory detail than in general I would expect you to have. So completing the square means I want to write it as a times x plus b squared plus c. And let's just, well, walk it out this way. So on the one hand, many of you have already completed this step in the problem. Let's FOIL it out and see what we get. A times x squared plus 2bx plus b squared, close parenthesis, plus c equals ax squared plus 2abx plus b squared plus c. And I want to choose a, b, and c so that these two things are equal. So I'm just going through completing the square in a purely algebraic context. So if this is the same as that, then the coefficients in front of x squared need to be the same. So this coefficient is limit of x squared is -1. So what does that tell you over here? Yeah, this will have to be a negative sign. So by looking at the square, Tom, I see that a has to be -1. So that'll give me negative x squared minus 2bx. Oh, there should be an a there, like distributive law. Minus b squared plus c. Cool. So the next thing to note is that the linear terms have to be the same. This 20 needs to give me that. So, because those two have to be the same, what fact can you tell me as a consequence? If 20 is equal to -2b, then yeah, b should be -10. Nice. So by studying the linear term, b equals -10. And let's just check that. 2 times -10 is -20, so that becomes a positive 20x. That's good. That's what it should be. Minus b is -10. And finally, the linear term. So I guess the linear term there is a 0. So what does that tell you about c? Ah, you said positive 100. I parsed it in my mind as 1,000 and 100 and was very confused about what you said.
Oh, okay. Yeah. I was just like, it cancels out the negative.
Yeah. Excellent. So we've completed the square. And hopefully that, in general, I wouldn't expect all of those WODs to be written, but hopefully that very algebraic technique helped to hammer home the things that we did too quickly last time. Okay. More examples are helpful. So, so area, which was -x squared plus 20x, is now the same as negative, x plus b, so x minus 10, plus c. Oh, neat. Now see, I lost the square form, but it's easy to graph now, right? It will look like x squared, but flipped upside down, shifted right 10 and up 100. So if I just wanted that vortex, I don't need to draw the rest of it, so I won't. So by looking at this graph, what is the maximum value for area that you see? 100. So the maximum area that Pacom can possibly achieve is an area of 100. It's achieved by x equal to 10. And in the original problem, what did x mean? It's one of the two dimensions of the rectangle. That's the parameter of x, so the ideal length is 10. There's another parameter of the rectangle that was given by y, right? Did we work out how to get y in terms of x? Yeah. We got this. So the ideal height, or maybe it's width and length, is also 10. What do you think? Should we include some units in this answer? Probably, if you want to actually give him informative information. So what units should be associated with the length? Miles. Because the original stuff was all in miles. We could convert to kilometers, but I think that would be a silly thing to do. The height, width, whatever, should be in miles. So what dimension should the area be in? Square miles. Groovy. So, on the other hand, this was the answer that if you just like thought for a second, you probably intuited. Right? What's the biggest rectangle you can build with a fixed perimeter? Well, it's probably the square, right? You make it long, you make the length bigger, but the area falls off. So, you should use your intuition, but it's nice to be able to check it doing something rigorous. So, now that we've gone through what I hope was a fairly explicit example, let's start to wax a little bit more technical. Let's abstract away some things so we can black box some of the analysis so we don't have to spend 20 minutes on each problem. Let's establish some things. So, I'm not going to, or maybe I should see, do people want me to rewalk the derivation of the completing the square formula? Does anyone want that? Okay, I don't see any hands. Okay, so let's just write it down. There's a general can formula you can have that completes the square. If you have any quadratic, ax squared plus bx plus c, you can complete the square to get that f of x is equal to a times x plus b over 2a squared plus c minus b squared over 4a. And if you want to check that, because maybe you doubt that I'm able to write a formula correctly, we can check it. Let's check it. We can check it by expanding. So that'll be a times, let's expand that out. So x squared plus x times b over 2a plus b over 2a times x plus b over 2a squared plus c minus b squared over 4a. And there should be a closed parenthesis somewhere, right? Fair enough. And now let's distribute that a and do some simplification all at once. A x squared plus x times b over 2a, x times b over 2a, that'll be 2 times x times b over 2a, and then that needs to be multiplied by a, plus b squared over 4a squared times a, minus c plus c minus b squared over 4a. And now I think we can just do some things just really quickly. So there's the thing that I needed it to be. Do you see an ax squared? I hope so. So that's good. There's my ax squared. That's nice. This term looks needlessly complicated, like it has lots of cancellation. There's a divide by 2 and a divide by a. There's also multiply by 2 and multiply by a. Oh, hey, there's x times b. That gives me this term. That's nice. How do people feel so far? All I'm doing is double checking the formula is correct. And finally, I guess this a will cancel with one of the a's in the denominator, leaving me with plus b squared over 4a minus b squared over 4a. So those will cancel, leaving me with the constant term. So ax squared plus bx plus c. So yeah, the formula is correct. On the other hand, if you just like remembering formulas, you can remember the formula. It's just nice to check that things are correct. Anyway, that was slightly tangential. The whole point is, this is now something that is easy to graph. It is a parabola, something that looks like y equals x squared. That a will stretch it and maybe flip it if a is negative. It will go left by b over 2a and up by that amount. So the resulting parabola will open up when a is positive, will open down when a is negative, and I know where the vortex will be. The vortex will be, well, go left by b over 2a, and we'll go up by c minus b squared over 4a. Oh, and I've painted myself into a corner. This is supposed to be upward opening. All right, so there's a picture. Let's read some things off from the graph. So if you want to see this graph, would you say this has a global max or global min? Global min, right? As x goes off either way, the y values will keep going up. So it's got a global minimum. And let's not worry about the y value right now. What is the x value that produces that global minimum? Groovy. And so the only difference when a is less than 0 is the graph will open, the parabola will open downward instead of upward. So you still have this vortex here at negative b over 2a, comma, c minus b squared over 4a.
But at that point, if a is negative and a is, and b is divided by 2, negative a, does that mean you can move to the right?
Yeah, but do I know that b is positive, or whether b is positive or negative?
Oh, okay. You just say that
Yeah, in whatever quadrant, that looks like it's in quadrant 2, but there's no need for it to be.
Okay.
The only thing that's honest in this picture is it opens up. So, same question. This time I see a global max at this vortex point, x equal to negative b over 2a. So, let's write down the takeaway. So that waxed a little bit technical, but let's pull it back to this idea of optimization. Any quadratic function, f of x equal to ax squared plus bx plus c, has its vortex at x equal to negative b over 2a. On the one hand, like that formula tells you what the y value of the vortex is. So I guess I may as well write it down. But in any given problem, if you want to remember how to find the x-coordinate of the vortex, you can find the y-coordinate by just plugging in the x value you found. So there's no need to remember the y-coordinate of the vortex. You can re-get it once you know the x-coordinate. When a is bigger than 0, or in this setting, the vortex minimizes. When a is less than 0, the vortex maximizes. So I guess if we know what happens when a is positive and when a is negative, let's just say something. What's the deal when a is 0? Yeah, it doesn't really have a vortex, does it? It's like a line. Nice. So, the big takeaway from this page is this fact. The x-coordinate of the vortex is negative b over 2. And the vortex maximizes or minimizes in the settings when you know it should maximize or minimize. Nice. So, the remaining things to do, I think, are some applications. So here's one. So let's suppose you have a secret that you need to keep. And you're going to keep the secret by acquiring some land in the desert by a cliff. And you're going to build a fence around this land, and then you'll bury your secret somewhere in that garden. Not speaking from experience, don't try to look for my buried secrets. Now, but you have a budget to walk in under. You've already acquired the land. You have enough money to buy 1,000 feet of fencing. You don't have to build a fence on the side that's already covered by the cliff. You're assuming no one's going to rappel down the cliff to find out your secrets. You're not that important. So you can save some money by not building any fences along the cliff wall. How much area can you capture? The bigger that shape, that region is, the more space you have to hide your buried secrets or treasure. Well, let's try to set it up. Let's try to optimize this problem. And we'll proceed in a way similar to the one we started with. We'll build a model. That model will be based on some quadratic formula that will appear. We won't bother finding the vortex. We have a formula for the vortex, so we'll use it. Good. So at this point, I think there are two options. I can talk through this example. I can give you guys some time to meditate on it, and we can come together. I guess those are the two options. And people would like me to keep talking through this one. Okay, seeing at least a few hands go up. If you want to walk with those around you and just figure it out, as long as you're not too loud or distracting, that's great. Let's talk through it. So, in order to build a model, this rectangle has two parameters, length and a width. I'm not very good with having clever variable names, so I won't try to be. Maybe L and W are better names for length and width. I'll just stick with X and Y. Now you have 1,000 feet of fencing. Can you turn that into some sort of equation? So 1,000 is equal to the total distance you can cover. Well, but in that diagram, how much fencing have you used with that choice of X and Y? Yeah, 1,000. Sorry, the thing I'm going for is what's the formula once you have X and Y? Yeah. Perfect. Yeah. Sorry, the question was too vague. So 1,000 is 2x plus y. Does that look like you could solve it for one of those two variables? Which variable would you rather solve for? Fair enough. It's the one that looks simpler. Y equals 1,000 minus 2x. Oh, maybe I should start with this. Before we go any further, what shape do people have any intuition for what shape they would expect to be optimal? I hear a call for a square. Let's see if it works. Well, I think it can't be a circle. That's not even allowed in the model. It might secretly be a better choice, but this model won't account for that. We can develop the techniques for that. I don't think we will, but one could. If you want to go further in optimization, the techniques of calculus that you'll learn when you take Calculus 1 will give you very powerful tools for optimizing that will let you get beyond just quadratic functions. Anyway, let's continue. So we want to maximize area. So let's set down the formula for area. The area of this region is just x times y. X times 1,000 minus x. 2x. Groovy. Does that look like a quadratic function? Let's think about the vortex formula. Flipping back to the previous page, or by thinking about the graph, will that vortex minimize or maximize? maximize. If that coefficient point of x squared is negative, this thing will be downward opening. The vortex maximizes. So the vortex will maximize, and the vortex is at, we have a formula for the vortex. It is negative b over 2 times a. So let's just sub in. What is b? 1,000. Oh, and it's negative. Divided by 2 times a. What is a? Negative 2. Nice. So this vortex is at x equal to negative 1,000 divided by negative 4. That's 250, right? 100 divided by 4 is 25. There's an extra 0.
That's 5.
Say again?
Oh. Never mind.
Yeah, so that's the trace of x. So there's the trace of x. The vortex formula that I wrote down does tell us the maximum output, but let's just remember this x. Let's go back to the original question. So the optimal rectangle has x equal to 250, and the original question I think was in feet, 250 feet. Do we have a formula that will recover y from x? That's 500, right?
Yep.
Awesome. So there are the dimensions of the optimum rectangle. So I guess it's not a square in this case. And I guess to some extent that makes sense. It's much cheaper for y to be big than is it for x to be big. Because you only need to build one side along with the length y. But the intuition wouldn't have told you that it should be exactly a factor of 2. All right, so there's the optimum rectangle. We probably want to know the area of that optimum rectangle. How do you get that area? Right, area is x times y, whatever x and y mean. Let's see, that's 125 and then 3 zeros, right? Oh, square feet. Cool. How do people feel about that? Does that go okay? So, with the time remaining, there's like 2 examples left. One of them is labeled as an exit quiz. We'll see how quickly we go. So, in the 2020 Marble League competition, a world record was, no, that's a spoiler. The gold medal in that competition was won by the Rangers fielding the marble mandarin. So let's just study some setup. So this competition amounts to like going down a ramp and then seeing how high the marble goes. That marble had an initial vertical velocity of 315 centimeters per second. Some corrections had been made. I had written down the wrong marble and the wrong velocity. Gravity is applied vertically, and at a rate of 10 meters per second squared. 1 meter is 100 centimeters, so that'll be 1,000 centimeters per second squared is acceleration due to gravity. Because of some of the terms that come from the calculus, you divide it by 2. There's the model that physics tells you the height of this marble will follow. At what time will this marble mandarin achieve their maximal height? What is the maximal height that this marble achieves? I guess in centimeters approximately. So, What do you think? Does this seem like a straightforward enough question? Slash, is there anything that I wrote which is not readable? Okay. So let's talk through it. It looks like I want to maximize the height, which is given by negative 500 t squared plus 315 t. Time measured in seconds, height measured in centimeters. So, does that look like a problem to which the vortex formula applies? Right? Well, it's something having to do with physics, so that it's going to like go up and then come back down. So it'll be a vortex it'll be a parabola that opens downward. The vortex maximizes. Let's find the vortex. So the vortex is at, well, the independent variable is not called x, it's called t, but the mathematics doesn't care about that. So the vortex formula is negative b over 2a. That's the time at which the vortex occurs. At this point, I've already forgotten the formula for the y value of the vortex. So that's how much I think that it's not important to have internalized all the time. The vortex occurs at t equal to negative b over 2a. And let's just see what those are. What is b in this context? 315. So negative 315 divided by a. So 2 times negative 500. And I certainly hope no one would have reached for their calculator to do that bit of division. Cool. So that's the time at which Mandarin achieves their maximum height. How can we now figure out what the maximum height this marble achieves is? Yeah. Yeah, this is the time when the maximum height achieves. We have a formula for the height at that given time. So the max height is the height at time equals 0.315 in seconds, but I'll suppress units here. Cool, so that's 315 multiplied by 0.315 minus 500 times 0.315 squared. Cool. And that's like enough digits that I certainly wouldn't want to approach it by hand. One could make headway by like doing some factoring. It looks like I see basically 315 squared in each term, but let's not bother with that. All right. 315 multiplied by 0.315 minus 500 multiplied by 0.315 squared. All right. So that was also enough things that I doubt my data entry, so maybe I'll do a combination of letting you see if I've done anything obviously wrong by entering that formula. Oh, it even agrees with what you got. Okay. Anyone wind up with something different? Groovy. Then I trust it. So the maximum height is approximately, I think it's exact actually, 49 point. No, let's approximate. I don't want to write down that many. So the marble's maximum height is somewhere around 49.6 centimeters. The previous world record in the high jump was established at 48 centimeters. Did this break that record? Yeah. Groovy. So, that problem hopefully felt really quite explicit at the end. If you want to optimize something that's quadratic, use the vortex formula. If you have a problem that seems abstract and geometric that you want to optimize, try to assign some parameters and work out a formula for the thing you want to maximize. If that formula works out to be quadratic, use the vortex formula. If that thing is, well, yeah, I think that's enough on that train of thought. So with 3 minutes left, here is one remaining question. The once law is selling needs, which is a thing which everyone needs. And hires on an economist cousin. That economist cousin, after doing some market studies, concludes that the revenue generated by the sale of needs will be given by the model, the revenue that we produce P needs is negative 1/2 P squared plus 1900 times P. I think probably measured in dollars. Though I don't know if Dr. Seuss ever establishes what currency is used. Does that seem like a problem that we can optimize? Yeah, I think so. And I'll give you guys 2 choices. Do you want to do it or do you want me to do it? Some people want me to talk to it. Cool. I will continue talking. This is a quadratic function that we want to optimize. So that means I can apply the vortex formula. What is the leading coefficient of this quadratic function? Negative 1/2, which in particular is negative. So will the vortex maximize or minimize? Maximize. That's good. We want to maximize. So the first thing the vortex formula says is the vortex maximizes. And we want to maximize revenue. So the vortex is what we want to find. And we have this vortex formula that says the vortex is at P equal to negative B over 2A. And I think I won't finish the problem, but I'll write it down. So that's negative 1900 divided by 2 times negative 1/2. Oh, I guess I should just finish that. So, if the once law wants to maximize revenue, now, oh, that was the price. The once law should set the price of a single need to 1900. Does the problem actually ask what the maximum revenue is? Do you think we could find it if we wanted to? Yeah, you just plug in that choice of price. But the problem doesn't ask for it, so I'm not going to do it. So, oh,